7 problems, $7 million each, and only one is officially solved. The others? Still out there taunting us. We're diving into how to tackle them, not with brute force, but with a sharp new lens, semantic mathematics. Think of it as giving these old beasts a new kind of X-ray. So what's the secret sauce? It's called the unified closure calculus. Sounds fancy, right? It basically says, if you can control the local bits, the small pieces, the specific examples, then maybe, just maybe, you can build a solid case for the whole thing. But it's not easy. You need 5 things to line up perfectly. First, compatibility seam. Your local findings must fit together seamlessly at different scales. Second, cohesivity or compactness. Nothing can escape to infinity, no infinite complexity, no runaway costs. Third, limit closure. When you take limits, you stay within the game. Fourth, resource preservation. Every step has a cost and we track it. And finally, escape modes. Knowing where things might go wrong, information loss, computational explosion, etc. Poincaré nailed it with Ricci flow and surgery, a beautiful chain reaction. The other 6, they're missing the decisive bridge. Let's talk P versus NP. Everyone knows the question, is finding easy as checking? Our angle, can a single clever algorithm generate all possible proof prefixes efficiently? The key is a uniform extension selector. Think of it as a super smart search engine that doesn't cheat. We ran some local tests, like checking small SAT problems. We saw the classic asymmetry, verifying is easy, finding the solution feels hard. But here's the catch, passing these finite tests, even showing black box limitations, isn't enough. It doesn't prove P is not equal to NP for any general algorithm. So 7 experiments passed, 0 new proofs. That 0 isn't failure, it's honesty. We can't jump from a few examples to a universal truth. Next up, the Riemann hypothesis. All those sneaky zeros of the zeta function. Do they all lie exactly on the line with real part 1/2? Our bridge involves the Weil explicit formula, specifically its gram factorization. Imagine trying to write a quadratic form as a perfect square, always positive. If we can do this for all relevant test functions, bam, hypothesis proven. We checked the first 30 zeros numerically, they're all guagui on the line. But again, checking 30 isn't checking infinity. Just because a pattern holds for a bunch of samples doesn't mean it holds forever. The gap is proving that positivity universally. This problem has a clear target, but the shot hasn't landed yet. Now for 2 heavy hitters, Navier-Stokes and Yang-Mills. Navier-Stokes asks, will these fluid equations always behave smoothly or will they blow up? Our bridge seeks a universal, coercive bound on vortex stretching, basically, keeping the whirlpools from getting infinitely intense. For Yang-Mills, the million-dollar question is the mass gap. Do these quantum fields have a minimum energy above 0? Our bridge needs a uniform positive gap from lattice simulations to the continuum limit. We ran local checks, a nice 2D flow, a positive gap on a tiny toy lattice. But these are just baby steps. A smooth 2D solution doesn't guarantee 3D chaos won't arise. A small gap on a lattice doesn't mean the gap survives in the real world. The challenge is making these bridges work everywhere, not just somewhere. So, what's the grand takeaway? We've got 7 problems, 7 proposed bridges, 7 successful local experiments. Looks great, right? Except 0 new proofs for the big 6 why. Because passing a local test, however clever, is not the same as proving a universal truth. That's the non-collapse principle in action. This framework, SEPTEM, gives us a map, a common language, a way to precisely identify what's missing. The next move? Experts pick up these bridges and try to hammer them out. This isn't the end, it's the beginning of a more focused attack. Thanks for listening.